Okay, now that we understood the importance of confinement in columns, we will look at two different scenarios. One is when we have small eccentricity on our columns, and one is when we have large eccentricity on columns. To distinguish these two cases, just remember a bridge which the actual force of the truck is exactly on top of the column underneath it, or the bridge which the cars or the train is happening in the middle of the road while the columns which are supporting the bridge are on the sides. For sure, in that case we have large eccentricity. When the actual force is exactly on top of the column, we have small eccentricity. So small eccentricity, the actual force is very close to the centroid of our column, although there might be some eccentricity, but it's very close to it. Large eccentricity when the actual force is away. In this case, due to this distance and due to this eccentricity, if you remember, actual force times its perpendicular distance will cause a moment in our section. This moment will be a flexural input to our column and can cause it for a flexural failure. So we don't have only the actual or the confinement issue, now we have the flexural issue as well. So we should do confinement plus flexural strengthening. While in a small eccentricity, we just have the confinement issue that we had. Now ACI, the American Concrete Institute, suggests this formulation, which is simply whatever moment is applied, which can be caused due to this eccentricity, over the actual force times its height of the section. Yeah, height of the cross section. Yes, this is not height of the entire column. This is height of the cross section. If it's less than 10%, you have small eccentricity. If it has higher than 10%, you have large eccentricity. So in any case, you just get the analysis outputs, the moments and the actual forces. You do a simple analysis and you see if they are less than 10%, we are dealing with small eccentricity and the calculation will be simpler. If we are dealing with large eccentricity, more than 10%, then not only confinement is an issue, we have to make sure that flexural strengthening is also satisfied so our column does not buckle. Now, first of all, let's just discuss about small eccentricity. This is the case which has less than 10% eccentricity. Very simple, we calculate the capacity of our RC column considering that there is no additional fibers or additional reinforcement to it. That capacity is presented by NRD and is simply by multiplying the area of the concrete cross section by its design capacity plus the area of our steels, longitudinal steels, times its yield design strength. And we just compare that capacity or resistance of our column with the applied actual force. If our resistance, which was calculated like this, considering the strength of my steel and strength of my concrete, as well as the area of my concrete and area of my steel, the column, if it's higher than my applied load due to the dead load and live load, confinement is not needed. Everything is fine. You can carry on with the calculations. But if that applied load due to the dead load, live load, actual load is more than your resistance, then you have a problem. The resistance is not good enough to resist all of your dead load and live load. Then confinement is needed. And then this resistance, now that confinement is needed and we have added the FRP, will become a new resistance. Now, as you can see, the D gets a little bit away and we have added 2 cc's in it. This is the confined concrete. So we have to calculate this formulation, which in a second you will see what is the formula, and for sure this should be higher than the applied one. Then you will be satisfied with the whole design. So this is the formulation and we're trying to make sure that this is happening. So if you remember, in the normal NRD, we had the area of the concrete, the strength of the concrete, the area of steel, and the strength of the steel. If you compare that formulation to this, which we have a confined concrete, now we have a partial factor, which is, because it's based on confinement, based on code, is 1.1. We have area of the concrete as always, and now we have FCCD. This FCCD is the same strength that we discussed, and it is for the confined concrete. It's not the normal design strength of the concrete that you always had. This is a new strength for the confined concrete and should be calculated using this formulation. Now, all of these points are easy to calculate and we have them. The only issue is FCCD. As you can see, FCCD formulation has FCD on both sides and F1 effective on one side. So let's see how each of these are calculated. So FCD is simply FCM, which is the mean compressive strength of unconfined concrete, over a factor of safety. This factor of safety is usually depending on the concrete that you're working in, and the code will give it to you. Now, this is simple to calculate. This is the normal FCD that we always had. The issue is the F1 effective. F1 effective, as you can see, it has a longer formulation. It has an KEffective, which is simply this. And each of these will have a different calculation. We have this rho F, which depending on the spacing and how continuous wrapping is applied to it, it will have different formulations. So if there is any spacing between the wrappings of your FRP, these are the formula that you will be using, whether the column is rectangular or square, or the column is circular. If there is continuous wrapping, meaning there's no space between the FRPs, depending on the cross section of the column, whether there is square or rectangle or is circular, you will use one of these formulations for the rho F. EF, as you can guess, it's the elastic modulus of your FRP, which the factory will tell you. And epsilon FD rid, we will see it in a second, as well as the KEffective. Remember, this should be satisfied in order for the confinement to be effective. If this bit of the formulation, which is, let's say, this bit of the formulation, is less than 5%, then your confinement is not satisfying, and then you have to improve the FRP that you're using. You have to increase, for example, the elasticity of your FRP or the thickness of your FRP. Now, we were concentrating on the strain as well as the KEffective. So KEffective, as you can see, is based on horizontal efficiency, vertical efficiency, as well as the inclination efficiency. Each of them has a formulation, and as you can see, they're very simple formula, and it really depends on the geometry of your cross section. For example, the width of your cross section and the height of your cross section, when the roundness are omitted from them. So you will have a degree for this R, and then you will get the H prime and B prime from it. AG is the gross area of the cross section, B times H. The vertical efficiency, again, if it's a continuous FRP wrapping, there's no spacing in it, KV will be 1. If there's discontinuity, then FRP wrapping will be done with this formulation. There's an example here as well. You can see a bit of FRP, nothing, a bit of FRP. So there's discontinuity and there's not a continuous FRP in it. The values are all given here as well as if there is any angle on how the FRP is applied. Sometimes, for sure, if you use a discontinued wrapping, you will use less material. That's less material means cheaper bill at the end. So sometimes, if the discontinuity can be applied and it is sufficient enough, you will save money, as well as your client will be happy as well. So discontinued FRP is a common thing as well. But the formulations of KEffective, the coefficients of efficiency, is a very simple formulation as well. Now what is left from that formula is the strain. So the strain of FD RID, or the FRP design strain, or the maximum FRP tensile strain, remember again FRP is just for the tensile, is a minimum of either 0.4% or this formulation. If you remember, this was the famous environmental factor that we discussed in the beam as well. Depending on whether your FRP is internally or externally, what is the material and how it's exposed, the environmental factor changes. There was this partial factor as well, which again, depending on the code, you will have a value. Now, what is important here is the strain Fk, which is the maximum FRP strain at failure due to rupture of FRP system. So this is the ultimate strain that you have, and simply is just done by this formulation. If you remember, elastic modulus was stress over strain. Now we have it the other way around. The strain is the characteristic strength of FRP that you have over its elastic modulus. Both of these comes from the catalog of your FRP, so you can simply calculate them. So now the minimum of 0.4% or the other environmental times the strain divided by a partial safety factor will give you the epsilon FD RID, which is the design strain. But the question is, why do you think this strain that we are dealing with is at failure due to rupture of FRP system? It's very simple, because after the rupture of FRP, there won't be any tensile strains from the FRP, and due to that there won't be any resistance of ductility as well as no confinement. So all of the tensile resistance will now be done by the steel reinforcement which are around your column. So let's summarize it. We understood first of all that we have small eccentricity, so it was less than 10%, comparing the applied moment, the applied actual force, and the height of my cross section. Then we checked whether the NSD, the applied actual force, is less or more than the actual capacity of my concrete section, which was a very simple formulation, and we realized that no, it's not. The applied is higher, so we need confinement. Then I calculated that long formulation, F1 effective, and then having that one F1 effective, I managed to calculate FCCD. I just replaced it in this new formulation, and now I have a new resistance. So instead of NRD, I have NRCCD, which is the confinement of the confined concrete resistance. For sure, if this is bigger than this, everything is sufficient and your section is now safe for that actual load which is applied to it. This is the approach that ACI follows. As we mentioned, any slide which you see the ACI logo is not part of your assessment. It's just for your information that how the American code deals with it, and it's very similar with the similar mentality to what we have discussed based on CNR code, which is the European code for retrofitting with FRP. Let's look at an example where we need confinement for a column with small eccentricity. I have a building, 2 bays, 2 floors, 1, 2, 3 frames. There are the details of my primary rectangular beams, details of my secondary rectangular beams, my rectangular columns, my mechanical properties are here. A factor of safety has been applied to them to give me the design strength. Remember, these are the mean values of concrete and mean values of reinforced steel. These are not the characteristic ones, these are the mean values. I apply a factor of safety and I get the design strength, exactly what you were doing with the characteristics. FCK divided by, for example, 1.15 or 1.5, you were getting the FCD. Because these are the mean values, I'm dividing them by 1.35, which is a factor of safety. This really depends on the code, so really doesn't matter what the value is. Some loads are applied to it, some dimensions. And let's see what the analysis of my software, for example, ETABS or SAP 2000, have given me. So for each floor, whether the column is in the left side, in the center, or the right side, it has given me the values of the M and the actual force. Remember, these are the reactions that the software has given me, so the signs might be a little bit different. And I have calculated, simply using the ACI formulation, the percentage of eccentricity to see whether it's large eccentricity or low eccentricity. If you remember, if it was higher than 10%, you had an issue, you had large eccentricity, which, as you can see, majority of them are, but in some cases, like this, the central column for the first floor, I have small eccentricity. So let's check that out, that confinement is needed or not. Confinement may be required if that applied NST is more than the capacity of my section. So I have to calculate the capacity of my section according to its cross section. This is the cross section of that floor in the center column, first floor center. So I have the values of FCD, FYD. I have the area of the steel. I have the area of the concrete. And I calculated the NRD. The center column, left and right. These are the values. I just put it over here. I knew that I am still concentrating only on the center column because the other two were having large eccentricity. Now, comparing the NSD, the applied, which I got from the analysis, to the NRD, which I just calculated, 1397, I can see that my applied is higher. So I have an issue and confinement is needed. The only point is I am still in small eccentricity, but confinement is needed. So now instead of NRD, I have to calculate NRCCD, the resistance for confined concrete. So we're still dealing with this column. This is the column, first floor center. And this is what we are dealing with. We have to make sure that the applied actual load is less than the resistance of my confined concrete. This was the formulation to calculate. If you remember A, C, A, S, F, Y, D, we already have calculated very simply. Gamma RD was a partial factor, so no problem. The issue was FCCD. Some properties of the FRP that I have used: the thickness, modulus of elasticity, and strength. These are what the factory gives you. And pay attention to the symbols as well. This is the process for calculating FCCD. If you remember, this was the formulation. And out of this formulation, I had to calculate FCD as well as F1 effective. F1 effective had this formulation, this long formulation. One of them was KEffective, coefficients of efficiency, which was horizontal efficiency, vertical efficiency, and inclination efficiency. In both cases, I have continuous wrapping. So based on the formulations that you just saw in previous slides, those have been calculated. Now I have to calculate rho F, the rho of FRP, which is the geometric strength ratio for continuous wrapping. Again, we're dealing with a continuous wrapping. We as a designer have decided that it will be a continuous wrapping. So rho F has been calculated very simply as well. And you can see it only depends on some geometry of the section as well as the properties of your FRP, thickness of FRP, B and H of your section. What is now left? Elastic modulus of FRP, you already have got it from the factory. They have given it over here, so no problem with that. The only thing left is this strain. The strain, we discussed that is a minimum of either 0.4% or this formulation, which had the environmental factor, some partial safety factor, as well as an epsilon, which you have to calculate based on the properties of the factory. So FFK over EF. Both of these have been given by the factory as well. So I'm just using these two to figure out what is the characteristic strain of my FRP. I put it in and I can calculate the epsilon in this case as well. I'll put all of those values back in here and I get F1 effective. FCD I have already calculated in previous slides. It was just FCK or FCM, the mean or the characteristic divided by a factor of safety. I have a factor of safety given separately to me, so I just divided them and I got the FCD. F1 effective, we just calculated it. So everything is done. I just figured out FCCD. Now I put it back in the formulation of N confined concrete resistance for the actual. I have this. I have the area of the concrete. I have the area of steel. I have the yield design of my steel. The only thing which was left was FCCD, which I just calculated it. I put it in, I get a new resistance. I now just compare this resistance to my applied load from the analysis. The applied load from the analysis was 1,407 kilonewtons. My confined one is now 1,622. I just use one layer of FRP, and with all of the properties, geometrical and mechanical properties that we had, the central column with small eccentricity will be sufficient and it will be satisfying. The same properties that the factory has given me. So we just try to make sure that this resistance is higher than this. This was the case that you had small eccentricity.